Thank you very much, and good afternoon, everyone. As Jennifer has already mentioned, my name is Farhad Huseynov. I joined CSIC about a month ago, and I've started working on Staffordshire Bridges performance monitoring of infrastructure using fiber optic sensors. And and today, using this opportunity, I would like to briefly introduce myself and talk about my previous research experience through several field testing campaigns I conducted in the UK, and briefly introduce the project I will be working on in the time ahead while at CSIC. Brief introduction about myself. I'm originally from Azerbaijan, but I've been living abroad for the past 15 years. I did my undergrad in Turkey at Middle East Technical University, and I obtained Master of Science degree from the Sheffield University. And last year I completed my PhD at the University College Dublin, where I worked on bridge structure health monitoring. I did research on bridge SHM field under supervision of Professor Eugene O'Brien. While doing a PhD at UCD, I was also working for a small university spin-out company named Full Scale Dynamics in Exeter, UK. And FSDL is owned by 3 professors from the University of Exeter: James Brown, John Paul Reynolds, and Alex Pavich, and it's specialized in testing, monitoring and assessment of large full-scale structures. And the emphasis of my role was basically to carry out field tests on bridges in the UK and in Ireland. And before joining CSIC, I was working for a consultancy company named RPS as a senior bridge design engineer in Cork. And previously I worked for several engineering companies as design engineer in Georgia and in Turkey. So overall, I have 8 years of experience in design, testing, and assessment of bridges. And today I would like to talk about my bridges HM experience through my PhD studies and during my employment at FSDL. First, some background information on my PhD research area. And I would like to discuss its primary objective. I conducted research on bridges HM methods. Most of the bridge structural techniques available in literature use either acceleration, strain, or displacement measurements to assess the condition of a bridge. There's a lack of study using rotation measurements, and it's because of the accuracy of commercially available inclinometers is not good enough to capture the effect of damage in a bridge, which was the main motivation behind my research area. So I started working on bridge condition assessment methods using rotation measurements under supervision of Professor Eugene O'Brien. To give some background theory on my research area that I worked on PhD during my PhD studies is based on the elastic beam theory. The change in slope between any 2 points on the elastic curve equals to the area under the curvature diagram, or M/EI diagram, between these points. So in theory, when damage occurs anywhere on the bridge, a rotation sensor should be able to capture its effect. But the main question, my research questions that I was working on is that will it be possible to separate the effect of damage from the entire rotation signal? And if so, is it possible to measure tiny rotations occurring on a bridge? And actually, what's the required accuracy to detect the effect of damage on the bridge? The figure on the left, the figure on the left shows the curvature response of a damaged bridge to a moving point load. So as the point load gets closer to the damage location, it can be seen from the figure that the effect of damage on curvature response increases. So basically, that's the main finding from this plot. And since the rotation is related to the area under the curvature diagram, so I proposed a damage indicator as a difference between the rotation response of a healthy and damaged bridge to a point load, or otherwise rotation influence line, which is the structural property of a bridge. And if damage, it's a structural property of a bridge, and it's the response of a bridge to a point load. The figure on the top shows the rotation influence line obtained at 3 locations A, B, C along the length of a bridge for healthy and damaged bridge states. Basically, the solid blue line represent the healthy state, and dashed lines correspond with the damaged state. And the difference between the rotation influence line is provided in the bottom plot. And as it can be seen from the plot, the peak where the peak occurs at the location where the point load is at the damage location, and it comes from this, basically the curvature plot. As the load is getting closer to the damage location, the effect of damage, it becomes more visible. So the most challenging part of my PhD research was to get accurate rotation measurements. The main operating principle of an inclinometer is to measure the angular rotation of a test specimen with respect to an artificial horizon. In my research, I used accelerometers that sense gravity, the natural reference for the horizon to measure rotation. So basically, the output of an accelerometer obeys a sinusoidal relationship, such as when it is placed horizontally, it measures 0g, zero gravity, and as it's rotated 360 degrees through gravity, it measures 0g. Let's say if it points upwards, it measures 1g, back to 0g, minus g, and then back to 0g. So the relationship, the output of an accelerometer looks like a sinusoidal plot. So in theory, the inverse sine function of the acceleration output should give rotation in radians. That was basically what I tried to test in a bridge, in a laboratory bridge at Exeter University, where I loaded the bridge with 500 kilograms and using a trolley, and I did 4 round trips. Basically, I pushed the trolley along the bridge 4 times, and the next plot shows the raw horizontal acceleration signal that I obtained during the test. I forgot to mention that I placed the accelerometers in horizontal direction. So it can be seen from the raw acceleration signal that it has a high frequency component, which is, I later found out that it is due to the longitudinal movement of the deck due to flexural bending. So as deck bends, it at the same time it shortens and elongates, so that accelerometer picks up that, senses that horizontal acceleration. What I did, I developed some signal processing techniques to remove that high frequency content from the total response, and the final result shown in the bottom plot, and this is the rotation. This is how I measured the rotation response of a bridge to a moving trolley, basically. I had a chance to basically, the first case study that I would like to present is the main purpose was to test this damage detection methodology that I developed throughout my PhD studies. Basically, I developed through numerical studies, and I tested the methodology in a laboratory at Kyoto University, and this was the final validation, and that I got a chance to test the proposed bridge damage detection methodology on a real bridge owned by West Somerset Railway. Throughout FSDL, full-scale dynamics, I did numerous field tests on their bridges, which helped me to build this strong network with the bridge owner. And as a result, he allowed me to test the damage detection methodology on the bridge. It's a relatively simple bridge. Actually, it's the most simplistic bridge I've ever came across. It consists of two main girders, and it doesn't have any railway ballast or concrete deck. Basically, railway lines sit directly on top of the main girders. And the conventional trains running on the West Somerset Railway, since it's the heritage railway, is steam trains. I think there should be a video image showing a steam train crossing over the bridge. Sorry, yeah, and as I mentioned, so the main purpose was to validate the bridge damage detection methodology I developed, but because it's a real bridge, it's not possible to cause real damage. Well, instead, instead of doing causing a damage on a bridge, I locally stiffened it, which is similar to applying negative damage on a bridge. And I stiffened it using steel plates. Is there any way I can? Yeah. Anyway, so I stiffened it using steel plates, where I clamped steel plates at the bottom flange of the main girders using bolts, high tension grip bolts, and I placed some strain sensors on the main girder flanges and on the top and bottom of the steel plates to test if the stiffening application was effective. And at the same time, I instrumented the bridge with accelerometers to measure rotation. During the test, I asked the train operator to stop on the bridge to test if the stiffening application was effective. So it shows the Raveningham Hall steam locomotive remaining stationary on the bridge, where we recorded strain at 3 locations, and basically the aim was to see if the full shear transfer is provided between the stiffening plates and the main girder, and to see if we will be able to get this nice linear strain distribution along the length of the bridge, which is quite linear, and it worked. I was very pleased seeing the stiffening application worked. Otherwise, if the plate slipped during the train loading, I would probably have a bigger problem than trying to finish my PhD, as the main girders have galvanized coating. And I was lucky enough that there wasn't any issue, there wasn't any damage actually caused to the bridge. So the plot on the left-hand side shows the raw acceleration data obtained from one of the sensors placed at the support location. I applied the same techniques to measure the rotation, and the rotations obtained from this acceleration response is shown on the right-hand side plot. I used the last portion of the signal, which is the response to a moving last bogie. So first, maybe should better explain what these peaks represent. The first peak represents a tender crossing over the bridge. The second peak is the biggest one, and it corresponds with the locomotive, which is the heaviest part of the train. And the following peaks corresponds with the 7 carriages, and the last peak is actually corresponds with a passage of a last bogie, which has 2 axles. There are some techniques available in literature to separate the contribution of each axle from the total response that I used throughout my PhD. The one that I used was developed by Professor Eugene O'Brien. And the figure on the bottom shows the total response from one sensor to a moving bogie, and this dashed green line shows the contribution of each axle. Since the weight distribution in a bogie the weight is evenly distributed, so contribution of each axle is the same. And I did this for healthy and stiffened bridge cases, and similarly the continuous line shows the measurements obtained for the reference bridge state, which is the healthy, assumed to be healthy, and the dashed red lines correspond with the stiffened bridge case. And since in this bridge, since the rail tracks lay on top of the main girders, we noticed that the sensors start picking up the rotations way before the axles arrive at the support location. So that's why the influence line of the bridge is much longer than the bridge itself. And the difference between the rotation influence lines is obtained from sensor A, is provided in the bottom right plot, where it shows this nice triangular shape which corresponds with the stiffening location, basically showing that the damage detection methodology worked on a real bridge. The second case study that I would like to present was conducted again on one of these West Somerset Railway bridges. It's a simply supported railway bridge. The structural configuration is slightly similar to one of the Staffordshire bridges, where it has a high skew and it consists of two main girders. The only difference is that this bridge is quite historical bridge. It's built in 1870s, so the main girder is made of wrought iron. And the purpose of the test was West Somerset Railway approached FSTL in summer 2017. They were hosting this famous locomotive, Flying Scotsman, which is heavier than the conventional train running on their on the line. And this mineral line railway bridge experienced, the abutment of the bridge was experiencing some vertical cracks on one of its wing walls, which and this is, yeah, so the video imaging here shows actually when the train was moving, it was with the bare eyes, it was possible to see the wall movements due to the steam trains. The figure at the bottom shows the gross weight of the steam locomotives running on the line. They're quite heavy compared to the modern trains in modern railways. The gross weight of the Ravonningham Hall or 7F class locomotive is 75 and 65 tons, whereas the Flying Scotsman is heavier than those steam locomotives. It has almost 100 tons gross weight. And bridge owner was interested to get the crack movement behavior of the wing wall. So before we did the test, he didn't have any idea if the abutment wall moves or if the movement is due to the movement of the wing wall and etc. Using this opportunity, it's a Flying Scotsman locomotive crossing the bridge. It was quite interesting to see that famous locomotive from a very close. And using this opportunity, so basically we did two tests. First, I should mention it. We did two tests, one in June 2017, few months before the Flying Scotsman arrived. And the main reason was to see if the crack movement of the wing wall remained in elastic range. So we compared the magnitude of crack movements to various trains, and as said, and the purpose was to see if it would remain in elastic range when the Flying Scotsman crossing the bridge. And using this opportunity, I also installed some sensors at the deck level, purely for academic curiosity. I placed these accelerometers in horizontal, oriented in the horizontal direction, to get rotation. And the purpose was the aim for was to use these rotations and calculate the deflected shape of the deck using polynomial fitting approaches available in literature. The figures, the plots on the slide shows the crack movements obtained at both sides of the crack line. The test point 1, which is the left side of the movement, actually shows the closer to the deck, closer to the abutment wall, and TP2 is on the right-hand side in the slides, where towards the end of the wing wall, and the figure shows that actually it's the abutment wall moves relative to the wing wall. This and the magnitude of movements wasn't significant, big enough, and which basically this plot is for the Raveningham Hall locomotive, and we obtained the same one for the 7S class locomotive. And during the Flying Scotsman, basically the magnitude of movements didn't vary much, which basically ensured the safe passage of the locomotive, Flying Scotsman. And the plots on the plot on the left-hand side shows the rotation. It shows the raw acceleration data obtained from one of the sensors placed at the support location at deck level, and the plot on the right-hand side shows the rotations obtained from these 5 accelerometers placed at 2 supports, quarter, 3/4 span location and mid-span location. I use this rotation data to calculate the deflected shape of the bridge, and but at the same time, I forgot to mention. Sorry, I attached some optical targets at the mid-span and quarter span locations, and this was monitored using the imetrum cameras. And the plot shows the mid-span and quarter span displacement time histories obtained from imetrum camera and from the polynomial fitting approaches using accelerometer or rotation data. And they show that basically the displacement obtained using the polynomial fitting matches the imetrum measurements quite well. For similar results for the Raveningham Hall passage and the other locomotive. And now I would like to talk about briefly introduce the project that I started working at CSIC. It's called Performance Monitoring of Infrastructure Using a Digital Twin. It's a part of an ongoing project. It's the 3rd phase of an ongoing project which started in 2016. It's called Staffordshire Bridges Performance Monitoring Using Fiber Optic Sensors. 2 bridges were instrumented using fiber optic sensors. One is the steel composite bridge, and another one is pre-pass pre-stress infill deck type bridge. And in the initial research objective in the phase 1 and phase 2 was to investigate fundamental structural response and evaluate sensor network robustness and establish comprehensive performance baseline. And the main objective of the 3rd phase that I started working on is to showcase for the use of real-time data analytics and integration with digital twins, translate all the monitoring data into information beneficial to bridge owners using the digital twin technology. Basically, I put some thoughts about how what kind of information a bridge owner would expect from such structural health monitoring techniques, and what kind of information would be useful to be integrated with digital twin. So the basic bridge design or bridge assessment criteria is to see load actions to be equal or smaller of the load capacity of the structure. So any input relevant to the bridge load conditions or relevant to the stiffness of the bridge, or in other words, load capacity, will be fed into digital twin, and the information from the digital twin will be something like if the bridge is safe, if so, what's the load factor of the bridge, and what's the remaining service life of the bridge, and so on. I read some studies which is all published on, which is already available on Staffordshire bridges, to familiarize myself in phase 1 and phase 2 of the project. Basically, most the available studies from the first 2 phases of the project mostly focus on permanent load actions, the effect of time-dependent load actions and material properties on structural performance, such as how the creep and shrinkage affects the whole performance of the structure, and how the accurate representation of the permanent load distribution along the length of the bridge of the stage deck casting affected the bridge performance, and so on, and then how the actual load distribution factors on the deck. And throughout the time, how the pre-stress forces, for instance, formed, which are basically time-dependent properties. And I put some thoughts about what can be done further, and I realized that the available studies haven't really addressed the load actions due to the live loading at the bridge site, and as well as the boundary conditions, although the bridges such as this steel composite and the pre-stress precast bridge within the project are designed as simply supported. There are some degree of fixed to always exist because they rest on elastomeric bearings, which has certain degree of fixity, and the accurate the representation of such behaviors could reveal significant strength reserve of the bridge. And besides, the live load actions provided in Eurocode does not represent the real traffic loading. Instead, load models are developed to reduce maximum load effects for a wide range of bridge types spanning from between 2 meters to 100 meters, at the same time a wide range of loading conditions. Hence, both assumptions are conservative, and the accurate representation have potential to reveal hidden strength reserve. That's what I started investigating, and it shows this very simplistic model of the IB5 bridge that I started working, and I have 2 ideas how the live loading could be the load actions of the live loading could be simulated using a digital twin. The first idea is to use bridge way in motion data. The figure on the left shows a bridge model. It's basically the concrete deck is hidden from the view. It shows only the main girders, and the bridge model is loaded with random axle weights. And the idea is to, using bridge way in motion systems, which use the strain response to calculate the vehicle of a traversing vehicle, it's possible to calculate the axle weights of the passing train, and then use that and then put the axle weights as a moving load into the digital twin to replicate the load actions due to moving trains. That's the one idea. But the disadvantage of this method is that it it requires an accurate axle detection system, which I'm still working on the various techniques how a presence of axle could be identified on the bridge. The second method is instead of using axle weights as an input into digital twin, instead of using axle weights, to put a displacements at various locations along the length of the main girders as an input into a FE model. So I did the simulations and load actions causing these deformations, and then if you input that deformations into a FE model, they should generate the same load actions, and which they did. And I also run I used a similar approach that I presented on Mineral Line Bridge, where the displacement deformed shape was obtained using the polynomial fitting, so basic integration of the rotation. I applied the same techniques to curvature data obtained from the IB5 site, and this shows the displacement at mid-span location obtained from the obtained using the imetrum camera and using the polynomial fitting approach, and it shows that they match pretty well, which I'm planning to use further to investigate the realistic load actions due to the train loading at the bridge site. Thank you very much, and if you have any questions, I will be more than happy to